Hi everyone, welcome back to Dave's Math channel. I'm your host David Tear. This video is my first in a new series called Math and Science. And today I'm going to talk about Avogadro's law and Avogadro's number. You guys may be familiar with this if you've studied, undergraduate chemistry or maybe even chemistry from high school. But anyway, let's begin. So I'll start by talking about Avogadro's law. And Avogadro's law pertains to ideal gases. What it basically says is if you have a gas container with a volume V of gas in it, and then and you let n be the number of moles of gas, and I'll talk about moles later. Mole is really just an amount of substance. It's a number. It turns out to be Avogadro's number, which is a huge number, about 6 times 10 to the 23rd. 1 mole is defined as uh, Avogadro's number of molecules of a gas. So if you have a fixed number of molecules of a gas, which we denote as n, then if you take the ratio V over n, that's a constant. Um, and there's different ways you can write this formula. But anyway, this is what Avogadro discovered back in the 18th century, I think. Avogadro, as far as I know, I think he was a French physicist. So he's known for Avogadro's law, which is really just a special case of the ideal gas law. This is a very important law in thermodynamics, by the way. I'm not going to go through this in detail, but it's a pretty simple law. It says if you have an ideal gas, which most gases are most of the time, then it says that PV equals nRT, where P is the pressure of the gas. Usually measured, there's different units of measurement of pressure. The SI unit is pascals, and Pascal is a very huge, or is a very small unit of pressure. It turns out 1 atmosphere, which is the pressure of the Earth's atmosphere, is about 100,000 pascals. Um, I think it's 1 Newton per square meter. That's a Pascal. And V is just your volume of gas in liters. And then N is, like I said earlier, the number of moles of gas. R is what's called the ideal gas constant. This is a physical constant. And then T, capital T, is the absolute temperature. This is the temperature in kelvins, degrees Kelvin, if you like. And the Kelvin temperature scale, in case you don't know, it's based on the Celsius scale or the centigrade scale. You just take the temperature in Celsius and you add 273, and that gives you the temperature in Kelvin. And it's absolute temperature because there's a thing called absolute zero. You can't, that's the coldest possible temperature. It turns out that yeah, you can't have any temperature colder than absolute zero, which is about minus 273 degrees Celsius, or about minus 460 degrees Fahrenheit. Very, very cold. Um, anyway, that's the ideal gas law. And I don't want to just talk about thermodynamics and ideal gases. I also want to talk about Avogadro's number because I already mentioned it. Here's the exact value. It's very precisely known. I guess it's defined to have this exact value. 6.0221407 times 10 to the 23rd power. It's a huge number. And it's really hard to grasp. I'll give you, some analogies to give you guys an idea of how big this number is. But it's a very useful number because it defines a quantity known as a mole. And it turns out a mole is just Avogadro's number of atoms or molecules. And this is very useful in chemistry, by the way. If you know how many moles of a substance you have, you can just multiply it by its atomic weight or its molecular weight, and that'll give you the number of grams you have. And this is very useful. This is used all the time in chemistry. By the way, Avogadro's number, or Avogadro's constant, as it's sometimes called, is not. Avogadro did not come up with this number. The guy who came up with this number was another French physicist named Jean-Baptiste Perrin. I think of 1906, early 20th century. He came up with this number, but it's named after Avogadro, I guess, because of Avogadro's law. which kind of uses it, even though it doesn't give a numerical value to it. Uh, but anyway, um, so anyway, that's Avogadro's number, and it's very, like I said, it's useful in chemistry because this is the periodic table. I'm sure you guys have all seen this. And there's something called the atomic weight or the atomic mass. I actually prefer the name atomic mass. It's not a weight, and the reason it's called atomic weight, it has nothing to do with weights that you weigh on a scale. The reason they call it atomic weight, it's a weighted average of the masses of all the isotopes of a given element. And it's a terrible name. I prefer atomic mass, even though it's not a particular mass of an atom. It's the average mass of all the atoms of every element on Earth. And you've all seen these on periodic tables. For instance, hydrogen, that's the lightest element. That has an atomic mass of 1.008. And you can read them off from this table. Every element has atomic weight listed on a periodic table. So if you know how many moles of a substance you have, you know how many grams. And I believe that the standard used for measuring atomic mass is carbon 12. A carbon 12 atom is defined to have a atomic mass of exactly 12. That kind of defines a unit of atomic mass. Anyway, so it's very useful in chemistry, not just in thermodynamics, but in chemistry as well. Whenever you're doing like chemical experiments, whenever you have to mix different chemicals or different substances, you have to kind of know how many moles of each substance you're using because you have to balance the equations. So that tells you how many grams you have to use. I'm not going to go into that in detail, but that's just some of the reasons why we care about moles and Avogadro's constant, Avogadro's number. So I thought I'd finish with some fun facts about Avogadro's number. I remember learning these when I was in college. I took a chemistry course in college about 40 years ago, and I remember our chemistry teacher. We had a really good chemistry professor, and I remember he taught us these particular facts here. So I'll just go through them. So, like I said, Avogadro's number is a huge number because it pertains to atoms and molecules, which are very, very tiny. The first fact, a stack of Avogadro's number of sheets of paper would stretch for about 6,000 light years, which is beyond the farthest star visible to the naked eye. And then Avogadro's number of grains of sand, if you spread them all across California, that would be as high as a 10-story building. And if you spread Avogadro's number of marshmallows across the United States, it would reach a height of 600 miles. And finally, I kind of like this last one the best. If everybody on Earth had Avogadro's number of pennies, then we'd all have $1 trillion. But life on Earth probably wouldn't be possible because we'd be buried under 50 feet of pennies. So anyway, that concludes my video for today on Avogadro's law and Avogadro's number. I hope you enjoyed it. Long live math, and I'll see you guys next time.